Hello everyone, welcome back to Chapter 8. We're going to continue our discussion of acids and bases and talk specifically about what happens when we are doing these neutralization reactions. We use something called titration, and titration is where we add the acid and base together, and we can actually do calculations to predict what the equivalence point, that is where your moles of acid and moles of base are equal, and also how much acid or base it would take to neutralize that. So in a titration, you have something in a solution that you know the concentration of it, and you react it with something that you don't know the concentration. And so a lot of times we call the known solution the titrant, which is going to be in the burette that we're going to be administering to a flask that contains the unknown solution. And so this burette is going to be marked, it's very precise, and it allows us to add small like drops of it so that we can precisely find what that amount is that we need to add. So in an acid-base titration, both of the reactant and the product usually are colorless. So what we do is we add something that will change color if the solution changes pH. And those are called indicator solutions. And they're usually like an organic molecule that we put in there that has a dye molecule attached to it, and it will immediately change color when you hit a certain pH. The end point of the reaction is where the indicator changes color. So that's where we see with our eyes that the end point has been reached. That is our estimation of equal moles of acid and equal moles of base. We select it because we want it to be specific where we think the equivalence point is. And the equivalence point is the exact place where the moles of H plus or acid and the moles of OH minus are equal. So the end point is an estimation by observing a color change using that indicator solution, and the equivalence point is actually the point. And they're usually so close together that you can assume that they are the same. Okay, so what happens in a titration is you have the burette, and it's this long tube, and it has lots of little marks on it. So like you have 10 marks in between each 1 milliliter. So it's accurate to a tenth of a milliliter, and you can estimate the 100th place. And so you put whatever you're going to titrate with into the burette. In this example, they've got the base in the burette, and then you have an unknown acid in the flask. You've added the indicator solution. Okay, so you've got acid and indicator solution. And the indicator we chose in this place is, since it's only acid in the flask, it's going to be colorless in an acid environment, and as soon as the pH goes above 7 or some base pH, it's going to start turning colors. As we add the base, you're going to, and usually you are stirring this, okay? So you're stirring it in between so you can get this good and mixed. And then when you start getting close to the point, you'll see some color right where those drops are going in, and then when you stir it, they go away. So that's how you know you're getting close, okay? And then when you reach the equivalence point, the entire solution will turn whatever color, in this case pink. So the titration is a quick way, especially in industry, for them to titrate things and estimate the concentration. And so this is just another way of looking at it. Now you want this color, and if you were in my lab, that would be too far. That pink would be too pink. Okay, they're using an indicator called phenolphthalein, and it changes from colorless to pink when it goes to a basic solution, and it shows you the equivalence point. But remember, we're looking at an end point, which is where the color change is, to estimate the equivalence point. So it's very important that we get this as pale pink as we can, because once it turns pink, it's going to just get pinker and pinker and pinker as you get more and more base in there. So that's why you want it to look more like that color pink than that color pink. Okay? And that allows us to estimate the equivalence point. Now, I know some of y'all look at the book a lot. Some of you don't. I am going to show you how the book calculates the concentration of the unknown acid. And then I'm going to show you the Dr. Kofeld easy peasy way, okay? And you can do it either way you want to, okay? The first way is with dimensional analysis. And dimensional analysis will always work for you, okay? So you can always depend on it. Okay, so this is going to be a reaction between hydrochloric acid and sodium hydroxide. And if you look those up, you will, or hopefully you remember at this point, that those are strong acid and strong base. Why is that important? Because then it's going to do what? It's going to ionize, but it's going to form the sodium chloride salt, which is soluble, and liquid water. So I don't have to worry about that there's still some left over or anything like that, okay? So I can just do the molecular formula in this case and do the calculation. So we're titrating 10 milliliters of hydrochloric acid, and we have an unknown constant in that, and we don't know what the concentration is, so I'm just going to put question mark molarity. And then, and remember, molarity is what? Moles of solute per liter of solution, right? Okay. And then it took, I'll underline these numbers, it took 12.4 milliliters of the 0.1 molar sodium hydroxide to reach the equivalence point, and it wants you to calculate the concentration of the unknown hydrochloric acid. So I have several numbers to choose from here to start with, and so how do I know what to start with? And oh, and make sure this is balanced, okay? Make sure you balance your equation, okay? Very important. Okay, so what am I going to start with? I'm going to start with whatever I have that would allow me to calculate moles, because everything reacts on moles. This is stoichiometry, if you remember stoichiometry. If you hated it and you thought you had escaped from it, you don't escape from it in chemistry, because stoichiometry is a lot of what we do. So I choose this to start with because I know that I can get moles from that, because I have a volume and a molarity. Okay, so I'm going to start with my 12.4 milliliters of sodium hydroxide, right? And somebody asked me about how I do the times when I'm doing these dimensional analysis, that they had learned in high school. They did this. Okay, they drew a line, and it's either way you can do it. Some people like to do the line because you can tell a little bit easier what's on top and what's on bottom, but you're still just multiplying things together. So if you recall, when we're doing dimensional analysis, we're gonna put on the bottom whatever we had in the top. All right, now what am I trying to get? I'm trying to get to molarity of the hydrochloric acid solution. So since I have a balanced chemical equation, I'm going to be able to use my molehill. Okay, so once I find out how many moles of one thing I have, then I can change it to moles of the other. So what I'm going to do is I'm going to say, okay, I got milliliters here. Molarity is moles over liters. So I need to change that to liters. So I know that there are 1,000 milliliters in 1 liter, and that got rid of milliliters. Then I put liters. Okay, do I have anything that has liters in it? Yeah, I do, because 0.1 molar is the same as 0.1 moles per liter. So that's the concentration of the sodium hydroxide. So 0.100 moles, right it above it, of sodium hydroxide. So that got rid of liters. So now I have moles of sodium hydroxide. I want moles per liter of my acid, my HCl. I have a balanced chemical equation where they are a 1-to-1 ratio. So for every 1 mole of NaOH, there's 1 mole of HCl, and I know that's 1, but I still write it because sometimes it's 2-to-1 or 3-to-1 or whatever. So I always go through that step. That gets rid of moles per sodium hydroxide, and that's going to leave me with moles of hydrochloric acid. So when I do all of my math, I'm going to get 1.25 times 10 to the minus 3, because I'm going to say 12.4 times 0.1 equals, and then divide by 1,000. And so that's what I'm going to get. Now, this gives me moles, but I want moles per liter. So I have to go back and remember how many liters did I have. I had 10 milliliters, and I'm just going to go ahead and say that would be the same as what? 0.01 liters. All right, so I'm going to take my moles and I'm going to divide it by 0.0100 liters. Might have just been 10, sorry. And that's going to give me 0.125 molar HCl. That's doing it by dimensional analysis that we're used to. So if you like it and that's your comfort zone, you can do all of these titration problems using this particular method. Just remember, you have to have a balanced chemical equation to do it. So you have to be able to write that equation, balance it, so that you can get your mole ratio correct. Now, I promised you that I would show you the Dr. Kofeld easy peasy way, right? Okay, so the easy peasy way is there is a formula, and it's kind of like the dilution formula. It's N sub A times M sub A times V sub A. So NMV is equal to N sub B, M sub B, V sub B. All right, N sub A, okay, is the number of hydrogens in the acid. And so N sub B, the number of OHs in the base. M is the molarity of the acid. V is the volume. Okay. So now I'm going to plug my numbers in. I don't have to have a balanced chemical equation. I don't have to convert anything to liters. All I have to do is I say, how many hydrogens are in hydrochloric acid? There are 1. Okay. What is the molarity? I don't know. So I'm going to write M sub A because that's what I'm looking for. What's the volume? 10 milliliters. That's going to be equal to how many OHs in NaOH? There's 1. What's the molarity? 0.100. And what is the volume? 12.4 milliliters. So I'm going to rearrange this and solve for m sub a. M sub a equals 1 times 0.100 times 12.4. That's just what was on the other side, right? Divide that by what was multiplied times the m sub a, 1 times 10. So the molarity of the acid is 0.125 molar HCl. So I got the same answer without having to balance the equation or doing the molar ratio, because I know the molar ratio in an acid base is just going to be dependent on the acid and the base. So you can do it this way or you can do it this way. Either way works. Okay. The first way, you need to balance that chemical equation so that you can get the molar ratio like you always use in a stoichiometry problem, and then you divide by the original volume in liters of the acid. This way, you take the numbers you have in your problem. These can be liters or milliliters as long as they're the same unit. So if it's already in milliliters, you can just leave them in milliliters. Okay, so that's how you calculate the unknown concentration of an acid when you're titrating with a known concentration of a base. So now you have some to try. Now, this is one that I show you because you may run into this at some point. And when we were doing hands-on labs, and when we do hands-on labs, a lot of times we do this. And so I've just given you how you do the stoichiometry if you use something like KHP. KHP is potassium. No. Yeah, sorry. Potassium. I had a blank there for a minute. Potassium, hydrogen, phthalate. That's the one that's not, I'm going to write down here because it's a real weirdo. Phthalate, okay? That P is not phosphorus, that's phthalate. And the reason I tell you that is because it would have a completely different formula weight if that was phosphorus. But phthalate is a particular polyatomic. So I give you the formula weight of KHP, and KHP is going to react on a 1-to-1. It's going to be 1 mole for every mole of base. Okay, so literally you take how many grams, because the reason this is different is because you're starting with grams of KHP in a certain number of milliliters, and then you are taking that through to the calculation. So you're not going to have to do this on the test or anything. I just wanted to show you so that you would not, if you ever see it as you move on and see other things, if you see that you're using this, and KHP is what we call a primary standard, which means you're actually weighing that to that usually you weigh it to like the 1,000th place, so it's super accurate. Okay, and then you compare that to how many milliliters of the sodium hydroxide. So this is how I standardize the sodium hydroxide that I use to titrate the acid. So that's the only reason that I'm bringing it up for you. And if you want to work it, you can, but it's not going to be you're not going to be tested on it or anything. Okay. and that is titrations of acids and bases.